And make sure I'm getting audio. Yep. Today is the 8th. There you go. Start that going around. Cade Bridges. No Garrett Cassat. Devin Graham. Jonathan Mercer. Cyrus. Ash. Jeffrey Snowden. Giancarlo. Chris Stuck. No. Dustin Taylor. Look right there on the corner. Giancarlo. Cody Wineland. Wade Young. Go. And Kayla. Everybody making progress on your makeup exam? Coming along? Anybody? Has anyone finished it? Turned it in yet? No? Say again? All right. So then everybody who has homework to turn in has turned it in. And let's get started on. Oh, here we go. Thank you. Thank you. Tell me what simple harmonic motion is. Somebody? Anybody? This is a sign-in sheet. Thank you. Everybody sign the sign-in sheet? You do. Up until now, when we developed those kinematic equations all the way back at the beginning of the semester, everything we've looked at, for the most part, has been I'm sorry. Oh, okay. All right. What's your name? Cody Winland. Well, the good news is, as long as it's alphabetized, you're easy to find. Right here. No, come on. I got some for you. That's. You signed the sheet? Thank you. And you do have the that makeup exam? Got it. Any homework to turn in? Not yet, okay. Now, when we started at the beginning of the semester, we developed those kinematic equations, and all of the forces and the vectors and everything we did was always based on one assumption: constant acceleration. Right? And we kind of moved away from that when we got to conservation of energy. And in fact, if you'll recall, in the conservation of energy lab, we specifically looked at the example of energy stored in a spring, and that spring getting turned back into kinetic energy. What was different about that spring as the source of the force causing the work to happen, causing the motion? Anybody? The spring did have a constant. Garrett. Yeah, don't sit down. I got stuff to give you. And just like Wineland, you're easy to find as long as it's alphabetized. It did have a spring constant, but it did not have a constant acceleration or a constant force. The force varied depending on good night. Don't bother to sit down. I got stuff for you too. And make sure you get the sign-in sheet signed. Oh, he's right on top. Right. The spring did not produce a constant acceleration, a constant force. And that meant that the equations of motion, those kinematic equations that we developed at the beginning of the semester, they won't help. Those were all developed under what special condition? That the acceleration was constant. Position might not be, but the velocity might not be, but the acceleration, the force, was always constant. Now, when you have a spring, you do have a spring constant, minus kx. That describes the amount of force that the spring is going to apply to whatever mass it's operating on. This negative sign right there, that is what makes it harmonic or oscillatory. That means, how do we, okay, we're going to, when you have a spring, we're going to have to introduce some new terms now because it doesn't work, because we're no longer dealing with those old equations of motion. So we're going to have new terms that we're going to have to understand. And the first one we're going to talk about is displacement, x. The very word displacement, what does that mean? If you'll recall from the early work, the very first things we looked at was, one of the things we looked at was the difference between distance and displacement. What was the significance of that? Somebody. Exactly. Distance was how far you traveled to get from A to B, but displacement was strictly the difference between the two positions. You'll notice I'm only using x, so we're going to work this in a one-dimensional issue for the time being at least. But x now is our displacement. Displacement from what? When we were dealing with kinematic equations with normal constant acceleration of gravity and forces, and displacement was how far you were from where? Where you started, from your starting point. Now, displacement has a slightly different meaning. It has a slightly different meaning because now we mean something slightly different when we talk about our starting point. And that is our equilibrium point. Equilibrium simply means that place at which all of the forces sum to zero and acceleration is now zero. If something is at equilibrium, it's static, it's not moving. Okay? Now, in the case of a spring, equilibrium is that what you would call the starting point, the 0 point, the point where the spring is not moving, it's not pulling and it's not pushing, it's just sitting there in its natural, untensed state, or its relaxed state. That would be equilibrium. When the spring is exerting no force on anything, it's at equilibrium. And now a displacement from equilibrium would be this x. Now, that's what x means now. So when you move away from equilibrium, from your 0 point, you're displacing the mass by some distance x away from equilibrium. As you move the box or the mass away from equilibrium, the spring now exerts a force on that mass. And this is the force that it exerts. It is the negative of a spring constant K times that displacement. So if you move the box to this position, X, the force that the spring is going to exert is now in the opposite direction. It's negative. That spring constant times this distance, X. You pull the box away from the spring, you let go, the spring is going to pull it back to its equilibrium point. If you push the box and compress the spring to some value of negative X, what force is it going to exert now? Force equals minus K times a negative X, which will be a positive K times X, meaning it's going to push the box back towards equilibrium. And this is the sign convention that we will use when we describe simple harmonic motion. So I say that negative sign is what makes it all work. However far away from equilibrium you pull or push the box, the spring is going to exert a force in the opposite direction back towards equilibrium. The book talks about makes the distinction that if negative Kx is the force that the spring exerts on the box, positive Kx is the force that you exert on the box in order to move it. Okay. What is all of this starting to sound a lot like? Let's back up just a little bit. We're no longer working with starting and finishing points. We're working with displacement as opposed to distance. Now, in this case, they're kind of the same thing, but what would that suggest to you that we are talking about displacement as opposed to distance? Anybody have a guess? Everybody think about it for a minute. I really would like somebody to come up with a guess. What does that imply? What did it imply when we were talking about a gravity field? It implies that it doesn't matter how far you move the box, that all that matters is the total displacement you have from, in this case, equilibrium. In the case of a gravity field, it was from whatever level you arbitrarily assigned the zero value to, or declared to be your ground potential. Now, equilibrium is well defined. It is ground potential is well defined. Our zero potential point is equilibrium. And any displacement you push or pull that box away from equilibrium, you are storing potential energy in that spring. Now, in the case of the gravity field, potential energy was mass times gravity times height, or displacement. In the case of a spring, potential energy is 1/2 kx squared. So if you move this box 5 inches or 5 centimeters or however far away from its equilibrium point, then the potential energy you store is 1/2 this constant times that displacement squared. I didn't give you all this yet. I'm going to go ahead and tell you now. The units of K are per meter, right? Yes. Newtons per meter. The energy you store in that spring will depend on how far you move it away. So if you move it 1 meter away, you've stored 1 Newton of potential energy. You've done 1 Newton of work to move it 1 meter, then it has a spring constant of K, of 1. What is this potential energy for a spring? What does that also look like? What does that look mysteriously like? Who remembers the formula for kinetic energy? And this should have let you, what you should be picking up on by now is that in order to analyze motion of a spring, simple harmonic motion, all we have to look at is conservation of energy. Okay. Now we'll still make assumptions like the box or the mass is sliding on a frictionless surface, so we don't have to deal with that, but deal with losses due to non-conservative forces. But basically, a spring is a conservative force. It is an internal conservative force. So picture what happens. You move this box away from equilibrium, some distance x. Now, as long as you're holding that box or it's locked into place, you have this much. You have 1/2 K times x squared of energy stored in that spring as potential energy. What happens when you release that box? The spring pulls the box back towards equilibrium, which means it is accelerating that box. This is important. It is not a linear acceleration. If you look at the force equals mass times acceleration, so we can divide out mass and just make it proportional to acceleration only. So whether you're plotting force or acceleration, you're going to plot the same kind of graph. That's a straight line. It's just a straight line moving up at a slope of K. What's the special name for a function that looks like this? That's just a straight line. Linear. It is a linear force. It is not a constant force. Okay? Now, Someday you get to some higher level courses in maybe graduate school or something, you might have to start dealing with nonlinear forces as well. But for now, we're just going to stick to non-constant forces that are still linear. Okay, we've released this box. Now all of that potential energy is being turned into motion. And the spring is pulling the box back to its equilibrium point. The spring is not going to bring it back gently and slowly. The spring is going to be exerting this much force to pull it back at the instant you let it go. If this is where you start from, then this is how much force the spring is exerting at the instant you let go. When the box moves back to here, and it's halfway back where it started from, at that point, this is how much force. So the box is still being accelerated. When you get to just a little hair off of equilibrium, just a tiny little bit away from equilibrium, the spring is still exerting a positive, non-zero force, which means the box is still being accelerated just a little tiny bit back towards equilibrium. That force does not get to zero until the box gets to zero. But you'll notice that at no point up until now has the spring been trying to slow the box down. To the contrary, it's been speeding it up the whole way. That means when it gets here, it has very much a positive non-zero velocity. How much velocity does it have? It's a constant. So whatever potential energy it had, so if when you've got it pinned to the track at that x displacement just before you let it go, its kinetic energy is zero, then all of its energy is potential. When it gets back to the 0 point, at that point, its potential energy is zero, which means all of its energy is now kinetic. And you find velocity by simply setting one half kx squared equals 1/2 mv squared, and you solve for v. Presumably at that point you know all of the other pop quiz. Right now. I said presumably at this point you know all of the other numbers that go into that equation. What is the most number of these variables that you can solve for using that equation? Somebody, we've talked about this. If you do not know K and you do not know V, how do you find them? And this is not just a physics question now. This is a general math question that will plug in the other numbers that you've got, and you still have two that you don't know. But that's my question. What's the most number of variables that you can solve for in that one equation? No. One. You have to have one linearly independent equation for every unknown variable. If you have 3 unknown variables that you need to solve for, then you need to have 3 independent equations. What does that mean, an independent equation? That means it cannot be an equation that you can derive from one of the other equations you've already got. Okay? The example, since most of you are in electrical and electronics, the example I like to use is Ohm's law, I equals E over R. Well, that's one equation. Well, I can also say R equals E over I and E equals I R. 3 equations, 3 unknowns, right? We can solve for all 3 of them. We can only solve for one of them because all 3 of these equations can be derived from the same equation. So you have, even though it's written in 3 forms, you only have one independent equation. That means in order to solve for any one of these variables, you have to know the other 2. Okay? This is a rule, it's a law, it's hard and fast, and it doesn't matter what class you're taking. If anyone asks you how to solve for multiple variables, you have to have one equation for as many variables as you want to solve for. In this case, we have one equation. We can never solve for more than one variable. Most we could do is solve for something like this, where we could write a function of one variable in terms of the other. But then we would get a separate value for the first, for every value we plug in of the second. Okay. Anyway, that's how you would determine how fast the mass is moving as it passes the equilibrium point. But as soon as it does, its displacement is now going to start moving into the negative territory, which means the force that the spring is exerting on it is now what? No. Once it moves past equilibrium into a negative displacement, what does that tell you about the force that the spring is now going to exert? The force will now be positive, pushing it back towards equilibrium. And it will continue to move towards a negative stopping point until it reaches that much potential energy. And you'll notice it doesn't matter whether the displacement is positive or negative. The potential energy is always positive anytime you move away from equilibrium. Unlike in a gravity field, where if you go below the 0 altitude, or whatever level of height you define as your 0 point, you can go to a negative potential energy. You can never go to a negative potential energy with a spring. Well, not without deforming it. But that's why this equation for spring potential energy looks mysteriously like the same equation for kinetic energy. You cannot have negative kinetic energy. You can't have negative spring energy. Any displacement is going to produce positive potential energy. And when it reaches that maximum positive potential energy, positive spring potential energy, its velocity will have fallen to anybody? How fast will it be going when this box goes all the way to negative x? When its potential energy is equal to the energy that it started with. Its velocity will be 0. Thank you. I'm not trying to trick you. That is simple harmonic motion. It is moving from a positive potential energy to a maximum kinetic energy to zero potential energy back to a positive potential energy. Basically, it looks like this. The ball rolling down and back up, and then down and back up, over and over and over again. And as long as it's a frictionless surface, it'll never slow down and come to rest. What would happen if it were not a frictionless surface? Yeah, it means that the friction is going to do work on the mass as it moves, so it's not quite going to make it back to here. It's only going to make it there. And then on the way back, instead of making it to here, it'll only make it to here. And then it only makes it to here, and then it only makes it to here, and to here, and to here, and to here, until it finally comes to rest at the bottom. That would be a slightly more complicated analysis to make, but not one that you haven't done. You've done this kind of analysis, just instead of the box and the spring, it was the roller coaster cart that didn't quite make it all the way back up to the other side of the hill. Do we have any questions so far? All right. Well, what does this oscillatory motion sound like to you? You've got potential energy. The thing drops to zero potential energy, where it immediately climbs back up to its maximum, and then back down to zero, and then back up to its maximum. And at the same time, it has zero kinetic energy here that climbs up to a maximum here, back down to a zero, back up to a maximum, and if I could draw better, it would look prettier. But what does that look like? Circular motion, sine waves, cosines. Exactly, it's oscillatory motion. And you'll notice that this is not a triangle wave. It doesn't go boom, 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 boom. It don't make straight lines because it is not a constant force. It's very specifically a non-constant force. Linear, but not constant. So, you would expect to find the same kind of terms to describe simple harmonic motion that you would find in any kind of sine wave motion or phenomenon, like an alternating current or something. So, what is this maximum displacement x? Yeah, it's the amplitude. Okay, minus x would be minus amplitude if we're talking 0 to peak. Okay. What would you call the time it takes for the mass to go from its maximum amplitude to its minimum amplitude and back to its maximum amplitude? That's your period. And 1 over the period is the frequency of oscillation. Now, in this case, we talked about the box sitting on a frictionless surface. Let's change that up a little bit. We can't quite come to a frictionless surface. We get pretty close with like air hockey tables, ice skating rinks. What happens if we take that same spring, instead of setting it on a surface and hooking it to a box, we hang it from a hook in the ceiling? Now, it's the force of gravity is actually stretching that spring. All that means is you now have a new equilibrium. Your equilibrium point now is where? How would you find this equilibrium point? We'll call it y since we're in the vertical now. There's our y naught. And let's say this is the y of where the spring would hang if it were not being stretched. How much spring potential energy is stored right there? Okay. You understand, we've let this box hang from this spring until it finally comes to rest, and it's just hanging there static. The spring is being stretched by gravity. So the stored potential energy of the spring is equal to 1/2 K y naught minus y of the spring, or y relaxed or whatever, squared. So you set the two equal, and you can determine where this new equilibrium position is going to be. Point is, if you go through and you do the math, they do it for you right here. It's on it's exercise B on actually figure 11.3 on page 294. And they tell you that mass times gravity is going to equal minus K, well, just delta Y. Okay. Mass times gravity is the force that's being exerted by gravity. And minus the spring constant times the displacement from its relaxed position is the force exerted by the spring. Once you have this new point, What changes? Nothing else. You now have a spring at equilibrium. If you displace the mass, you pull it down by stretching it, or if you push it up, you displace the mass from that equilibrium point and let it go, it's going to sit there and bounce. It's going to go from this potential energy to its equal and opposite potential energy, or position displacement of equal to an opposite displacement of equal potential energy, passing through maximum kinetic energy at its equilibrium point. Does anybody have any questions? Does anybody have any questions from their homework assignment? No? Does anyone else have any more homework they're ready to turn in? You do? All right, well, I'll get it from you anyway out. The next part of this chapter we're going into is going to be on the period and sinusoidal nature of the simple harmonic motion. We're going to start getting into, how many of you remember when we used pendulums in the labs to measure the force of gravity? Well, now is where we're going to start developing the equations that we used to do that. And we're going to look at how waves, oscillations or waves, how they can propagate and interfere with each other. I don't know how much I can do in 6 minutes. So somebody ask a question. What's the meaning of life? 42. Yes. Next question. Okay. Who else? Does anyone else get the reference? Okay. Say again? Yeah, it's from Hitchhiker's Guide to the Galaxy. Yeah, the white rats. Or white mice. Yeah. Well, then I'm going to let y'all out so y'all can go get busy on homework and makeup exams.